A new semiconductor device with AI simulates the human brain. The result is a transistor that reacts 10,000 times faster than human synapses. A research group led by Professor Kwon Hyuk Jun from the Daegu Jeongbuk Institute of Science and Technology, South Korea, has developed a new generation semiconductor artificial intelligence technology that simulates the efficiency of the human brain in neuromorphic transistors. The scientific article was published in Advanced Science. The development of artificial intelligence has stimulated the rapidly growing demand for energy-efficient semiconductor technologies with high operating speeds. However, traditional computing devices with their separate computing units and memory blocks have disadvantages in speed and energy efficiency. The human brain can calculate and remember simultaneously on one device. For this reason, more and more scientists and engineers are trying to replicate these capabilities in electronic devices. The authors of the new work created synaptic transistors using hafnium oxide, which has strong electrical properties, and thin layers of tin disulfide. As a result, a neuromorphic device was created that can store multiple levels of data, similar to neurons. The study successfully reproduced biological characteristics, such as long-term and short-term memory. The result is a highly efficient device that reacts 10,000 times faster than human synapses and consumes very little energy. Professor Kwon Hyuk Jun. It is expected that in the future this innovation will find application in various fields related to artificial intelligence and machine learning. In recent years, artificial intelligence (AI) has become a part of our daily lives, from simple applications to complex research and development systems. However, AI capabilities are limited by the speed and efficiency of existing transistor-based semiconductor technology. Synapses in the human brain, which are a key element in learning and memory, are able to carry signals through neural networks with high speed and complexity, making them a source of inspiration for the next generation of semiconductor devices. A research group led by Professor Kwon Hyuk Jun from the Daegu Jeongbuk Institute of Science and Technology, South Korea, has made a breakthrough by creating neuromorphic transistors that mimic the behavior of synapses in the human brain. The results were published in the scientific journal Advanced Science. These devices are capable of responding to input signals 10,000 times faster than biological synapses, which opens up potentially new horizons for the field of computational electronics and AI. The developed transistors show not only a high reaction rate, but also lower power consumption compared to traditional semiconductor devices. The use of a new semiconductor material with an effective system for simulating neurological functions opens the way to the creation of faster and more efficient neural networks, which can significantly accelerate the development of AI capable of more complex and deep learning. It could also lead to the development of new and more advanced forms of neural interfaces for integration between machines and the human brain. Such technologies can be used in a wide variety of fields, from medical devices that can mimic the nervous functions of the body to treat diseases, to the creation of super-powerful computer systems capable of processing huge amounts of data with incredible speed and accuracy. The key point in the work of Professor Kwon Hyuk Jun and his team is the use of innovative materials and technologies to create a new generation of transistors. Their research could usher in a new era in the semiconductor industry and artificial intelligence, where speed and efficiency will be brought to a level that previously seemed unattainable. As artificial intelligence (AI) continues to integrate into our daily lives, the pursuit of hardware that can imitate the human brain's efficiency remains a top priority for scientists and researchers worldwide. The research group led by Professor Kwon Hyuk Jun from the Daegu Jeongbuk Institute of Science and Technology (DGIST) in South Korea has made significant strides in this realm. Their groundbreaking work focuses on neuromorphic transistors mimicking the human brain's synaptic efficacy, with their findings published in the prestigious journal, Advanced Science. The team's achievement lies in the development of a semiconductor device that operates at speeds 10,000 times faster than a human synapse. This represents a monumental leap forward when considering the speed at which biological synapses transmit signals through neural pathways. The potential applications of such a device in computing and AI systems are immense, promising profound changes in the field of computational electronics. Neuromorphic computing has long aimed to emulate neural networks' parallel computing capabilities and low-power operation. The novel semiconductor technology from Professor Kwon's team addresses both aspects, offering not only a much swifter response to stimuli but also significant energy efficiency advancements over traditional semiconductor devices. This new class of transistors utilizes cutting-edge semiconductor materials, which have been specially engineered to mimic the synaptic action. By simulating these neural functions, the team has opened a pathway to creating faster and more complex neural networks. These can accelerate the development of AI capable of deeper learning and more sophisticated interpretations of vast data sets. One of the primary benefits of these neuromorphic transistors is the potential for seamless integration with biological neural systems. This would herald a new era of medical devices capable of mimicking bodily nerve functions or interfacing with the human nervous system to treat diseases. Moreover, these advancements could lead to the advent of super-powerful computer systems capable of processing large volumes of data with unprecedented speed and precision. Indeed, the work of Professor Kwon Hyuk Jun's research team may well be a significant stepping stone towards a new era in the semiconductor industry and artificial intelligence. Their research suggests a future where the speed and efficiency of brain-like computing become a tangible reality, effectively bridging the gap between electronic devices and the human brain. As society edges ever closer to developing true AI, the need for hardware that can keep pace with such software becomes increasingly critical. The neuromorphic transistors created by Professor Kwon's team might just be the breakthrough needed to fuel the next wave of AI evolution, laying the foundation for a future where intelligent machines and human-like computing can flourish side by side. Continuing the exploration of this breakthrough, let's delve deeper into the specifics that make these neuromorphic transistors so revolutionary. The research by Professor Kwon Hyuk Jun's team, which commenced in early 2019, culminated in a series of tests conducted throughout the latter half of 2021. These tests incontrovertibly demonstrated the transistors' ability to outpace the signal transmission speed of biological synapses exponentially. The results, published in the 2021 issue of Advanced Science, reveal transistors with a response time measured in mere nanoseconds, a stark contrast to the millisecond response time exhibited by the fastest biological synapses. To put this into perspective, a neural synapse operates at speeds up to 0.1 milliseconds, whereas these advanced semiconductor devices operate at a staggering 0.00001 milliseconds. The potential implications of this 10,000-fold increase in speed are monumental for the field of AI and computing. Energy efficiency is another important aspect brought to the forefront by these cutting-edge transistors. Where a typical synaptic event consumes approximately 10 femtojoules of energy, the semiconductors developed by Professor Kwon's team have shown to operate on an estimated 0.1 Fj per event. This impressive energy statistic not only translates into faster processing speeds but also supports longer battery life in portable devices and a reduced environmental impact for larger-scale computing operations. Perhaps one of the most striking figures to emerge from the research is the device's potential synaptic density. The human brain possesses around 100 trillion synapses, a number that makes its computing power and efficiency possible. The team's advances suggest a pathway to semiconductor devices with synaptic densities approaching this biological benchmark. As of the 2021 findings, the technology enables a density that could feasibly accommodate up to several billion synthetic synapses on a single chip no larger than a couple of square centimeters, showing promise for even denser configurations in the future. In terms of real-world application and impact, these figures are not just impressive in isolation but are heralding a new age of possibilities. With the advent of 5G technology, famed for its potential to offer download speeds over 1 gigabit per second, the need for equally fast computing hardware has never been clearer. Neuromorphic transistors like those developed at DGIST could be key to unleashing the full capabilities of 5G and beyond, allowing for real-time data processing and artificial intelligence operations at unparalleled speeds. Furthermore, predictions indicate that by 2025, the number of connected IoT, Internet of Things, devices will exceed 75 billion worldwide. The integration of neuromorphic transistors capable of ultra-fast data processing into these devices could significantly optimize efficiency, responsiveness, and the overall effectiveness of the IoT ecosystem. As research progresses into the 2020s, the numbers continue to illustrate just how influential these neuromorphic transistors could become. From transcending biological limitations of speed and efficiency to fostering the synergy of AI with human-like processing capabilities, the robust foundation laid by this groundbreaking research points toward an exhilarating future for AI, computing, and the integration of intelligent systems into daily life.